Hey team, I'm Maddie, welcome to Science Side Up, and today we're going to talk about how the atmosphere moves heat and air around and why that's important for our climate. So far, when we've been talking about Earth's climate, we've been talking about the Earth as a whole. What is the average overall temperature? How much does CO2, doubling CO2 raise average temperature over the Earth? But I want to start getting at what does that mean for, what does climate change mean for Southern California or for the polar regions or things like that? So getting into more of these regional effects and understanding why the climate system is going to affect, say, the Sahara Desert different than Antarctica. So to do that, we've got to start with some basics of how the atmosphere moves energy around. So let's start with this. This line represents the Earth. Here's the equator, EQ. To my right, this is the North Pole. So we've got Santa over there, and down here, here's the South Pole, SP. Not for spelling, which is not a thing I can do, but for South Pole. So, if you'll recall, the Earth is a sphere. I know, super complicated, right? But because the Earth is a sphere, sunlight doesn't hit all parts of the Earth equally. So the equator gets more incoming radiation than the poles, meaning it's hot at the equator and cold at the poles. Now that creates an imbalance, right? So if it's hot here and cold here, cold over here too, then we have an imbalance of energy. That's not a thing nature likes. Nature wants to bring things to equilibrium. So what does that mean? What that means is that we have created a mechanism, we have a temperature gradient, right? And just by the fact that we have a temperature gradient, we've created a mechanism for transport. So air from the equator is going to want to move away. Now I'm actually not going to draw that arrow because that would be misleading. But we're going to have a net transport of energy from the equator to the poles. So if, let's say, the sun turned off tomorrow and we waited a while, then what would happen, right, is that the temperature of the Earth, our atmosphere, it would become well mixed. And we would end up with eventually, we would end up with an even temperature everywhere. But there's other things in motion. We have a constant input from the sun. That input isn't even. So we have this just kind of permanent temperature gradient, which drives permanent circulations. So now that we kind of understand the driver, the mechanism of what's going on, let's talk about the Hadley Cell. Okay, team. So we've got our planet back, same setup as before, but now we're gonna think about sort of what air is doing. And for now, just for now, we're going to pretend that the Earth doesn't rotate. And you'll see where that comes into play here in a minute. But this is what's going on. We're heating up the air here at the equator. What does warm air do? Warm air rises. So we have rising air at the equator. By the way, this is also why you would see lots of clouds. Clouds also form when you have rising air. So we get lots of happy clouds here where we've got our rising air. And then once the air rises sort of to a point where it's going to be more neutrally buoyant, fun words, this air is going to start to travel polewards. So north in the northern hemisphere, south in the southern hemisphere. Now, if the Earth wasn't rotating, then this circulation would continue all the way up to the North Pole, where it would then, so it's cooling as it's moving towards the poles, moving north and south. What does cool air do? Well, cool air is gonna sink. So we would have sinking air, and then it's gotta go somewhere, right? So it would return to the equator. I'm drawing these in dashed lines because this is what I want you to think about for a non-rotating planet. And this type of circulation is called Hadley circulation. I thought my mic fell off for a second, but no, it's still there. Hadley circulation. And what this would act to do on a non-rotating planet is redistribute energy. Take this heat, this warm air from the equator, bring it polewards. And this whole thing, think of it as like a sideways lava lamp that works in two directions, right? So we've got, here's the base of our lava lamp, right? And then here's the base of our South Pole lava lamp. And then we've got blobs that do blobby things, right? And when they reach the top, they get heavy and sink. That kind of thing. So conceptually, that's all that's going on. And so that is kind of our base level of atmospheric transport. But what about Earth's circulation? I definitely meant to say Earth's rotation. Well, Earth circulation, this gets us into conservation of angular momentum. So let's bust out our slightly deflated globe, shall we? I still have this yarn taped to it from talking about the jet stream. Cool, so on our slightly deflated globe here, slightly deflated globe. All right, if we are on the equator, I'm gonna turn it sideways. So over here, we're on the equator. If you are standing on the equator, you are traveling at exactly the rate of the Earth's rotation, right? But notice, since our globe is a sphere, if we move towards, say, the North Pole, this latitude circle, this distance around, is less, right, than this, okay? So, if I am a parcel of air here, where's the equator? I lost it. Here it is, here's the equator. If I'm a parcel of air here, or like a person, maybe a balloon, let's think of it as a balloon. If I'm a balloon, a hot air balloon, and I am here, and I'm not like powering myself, I'm just moving with the planet, versus here, right? Sorry, team. Coordination. I gotta work on it. Okay, if I am here versus here, in order, and let's say we're hovering just above the ground, right? If we think about how fast the Earth is rotating under us, right? This guy, my hot air balloon at the equator, actually has to move a little faster than my guy hanging up in, the Middle East, right? Here, he's at the, what sea is that? It's written in Spanish, never mind. I did get this globe in Ecuador. Okay, my Spanish isn't that good. So the concept here, team, is that because of, if a parcel here and a parcel here are going to end up at the next longitude line at the same time, my guy at the equator has to move faster than my guy up north, right? This distance is greater than this distance. I hope that kind of makes sense. So when I'm taking air from the equator and I'm starting to move it towards the pole, I bring that momentum, that speed, with me. So we're gonna take our blob of air, right? We took a blob of air from the surface and we moved it up here, and then we started moving it towards the pole. So we started moving it here. this is the point where I wish I could like make this 3D like I was Iron Man or something, but I can't. So, but what's happening is that if we think of this air blob relative to, say, the air blob that started here, right? This is just what was here. This isn't what we moved. This guy is moving out of the board, right? Because if we think of it, we're gonna think of rotation, like moving with the Earth's rotation as movement this way, out of the board. So this guy is moving out of the board relative to this guy who is looks like he's sitting still compared to my equatorial air mass that I moved northward, right? So he's got this angular momentum, right? He's trying to move faster out towards us, wants to punch me in the face. So what that does is and this happens because the Earth is rotating. And it's because we have that rotation, we have this angular momentum that our atmosphere also has, and we have to conserve that angular momentum. So what we get in actuality is not a like equator-sized convecting cell. In reality, the cell breaks down at about, this is at about 30 north and also 30 south. So this guy, it's the same process. We heat it, it rises, it moves poleward, it cools, it sinks, and then it moves back. But because of that angular momentum, conservation of angular momentum, it breaks down at about 30 degrees. And that is something that is like unique to planet Earth. If we were spinning faster, this cell would become shorter, like more compressed. If we were spinning slower, it could move further north. So this is very much a function of our rotation rate. So this guy that I've drawn in red is called the Hadley Cell. Hadley Cell. We have a North Pole, Northern Hemisphere Hadley Cell, and we have a Southern Hemisphere Hadley Cell. And then we actually have two more cells that I'll talk about in the next video. But there's one more thing I want to talk about with the Hadley Cell, and that is the general weather that we see at the equator and at about 30 north. So we already said that when we have this massive rising air, we tend to get clouds. What do clouds bring us? Clouds give us rain. So we get near the equator, it's very rainy. But where we have descending air, this is actually associated with high surface pressure and very little precipitation. So I have a surface low pressure here. Low pressure is generally associated with precipitation, with big cloud systems and rain. And I have a surface high here around 30 north and 30 south. So we would get specifically no clouds, not a lot of clouds, not a lot of moisture, not a lot of precipitation. I need my globe again. Check out what happens if we just kind of trace 30 degrees north around the equator, or excuse me, around the globe. So I hope you can see this. Equator 10, 20 to 30, right? So that's between 20 and 30. There is the Sahara Desert. There is Saudi Arabia. There is, we'll keep tracking. In the States, we get, that's where we're gonna get like the desert in Southern California, deserts in Mexico, even like parts of New Mexico and Arizona. So global regions that we know to be desert regions fall right along this descending leg of the Hadley Cell, which that descending air producing high surface pressure leads to low precipitation. So just by understanding a lava lamp, right, we can actually understand why the Sahara Desert is where it is. And we'll talk about that more as we talk about regional climate effects moving forward. Okay, team, that's all I've got for you today. In the next video, we will talk about what goes on north and south of 30 degrees. What else happens in global atmospheric circulation? And then we'll move on to regional climate effects and climate feedbacks. I'm very excited about it. I hope you are too. So I hope you are well, and those you care about are well. Please like, subscribe, don't forget to be kind, and I will see you all next time. Bye, team.